taught in high school.
Dean Huffman from Vista Ridge. We're about to talk to you about accuracy and precision.
All right, let's do it. There's, in every measurement you make, some level of uncertainty.
And we're going to describe it in two ways. The first one will be accuracy. How close you are to the original target.
Right, you have some real actual value that it should be theoretically, if you could measure perfectly, you get this answer. And if your measurement's really close, then it's very accurate.
It's like hitting the bullseye.
Yeah.
Our next one will be precision, and that's how tight of a group they form, how close they are related to each other. Not necessarily the correct value, but how close they are to each other.
Right, so hopefully your measurements are both accurate and precise, that not only can you hit the bullseye, but you can do it every single time.
If you're a sharpshooter or you're sighting your gun, this is a must.
Right, and if you're a pitcher in the Major League Baseball, that's what they want from you. You want to throw strikes. All right, so let's look at a target and see what we mean. If we're neither precise nor accurate, that means we go all over the place here.
And you can't get a lot of information from this. This has got to tell you that you kind of need to start over or start changing one thing at a time because you got a lot of problems here.
Right, your experiment hasn't been designed well if your data looks like that.
Okay, now we're accurate but not precise, which means that we're getting very close to the target, but we're not getting very close in the same way every time. It's all over the board, as you can see.
Right, and if you'll notice here, the distance from this one to this one is the same as from here to here, so those errors cancel each other out, and your average is going to show you that you're very accurate, but your measure of precision is very low.
All right, now this is precise but not accurate. We're hitting the same spot over and over again here, but it's not towards where we want, or at the bullseye. So if you were using a rifle here, you would adjust your scope to bring it down and towards the center, and then you would be back to accurate and precise.
Right. Or you might just adjust your aim. This is how I shoot in archery every single time, so I have to aim down and right to hit the target. Yep. Okay, what if you hit the bullseye every single time?
You're on. You've got precision and accuracy, and everything is looking good.
Right, this is exactly what we want from every measurement that we make in the lab. So let's talk about how to measure accuracy. How do you know if you're doing it right?
One of the easiest ways to do it is by determining the error. That's a very simple calculation. You take the measured value, the value that you get in the lab, and you subtract it from the correct, well actually subtract the corrected value from it, and the corrected value is what you believe it should be.
Right, so we know that water should boil at 100 degrees Celsius, right? But in Falcon, it tends to boil at 92. So we would do our measured value in Falcon minus our theoretical value, and we see that we have a negative 8 for error. That means we're boiling 8 degrees less than what we expected. Okay, what's next? We lost our words. Keep going. Oh, here's how I explain it to my students. Basically, to find out your error, you say what you got minus what you should have got.
It's kind of like the test scores on a test. You should have got 100, but what you got was 88.
Right.
So the experimental error can be calculated from that.
Right, 12% mistake.
There you go.
Okay, so let's look at percent error, because some tests, if you miss 12 questions, you can get an 88% and that's good. But what if there's only 15 questions?
You're in trouble now.
Yep, you got a 33% on that. So what we're really looking at is how critical is that error? Like, is it a really bad error or just a small error in the grand scheme of things? So we use percent error for that.
And percent error is easily calculated. The error that you calculated.
Right, the absolute value, because it doesn't matter if you're too high or too low, it matters that you messed up, right?
And that would be that negative 8, absolute value 8, divided by 100, which was the accepted value,
Right.
times 100%.
Oh, well that error, percent error is easy math, right?
That's right.
8 divided by 100 times 100. So we had 8% error in this one.
Now we're going to take a little bit tougher look. We got an experimental value of 1.24 grams. The accepted value is 1.30 grams, and we're going to do the same type of a calculation.
Okay, so let me make sure I do this right. We take our what you got minus what you should have. And then we want the absolute value for that. Okay, can you run my calculator for me? All right, so do 1.24 minus 1.30, and then we divide by what we should have got. The accepted value was 1.30.
So we've got 0.06 divided by 1.30, and we should have got 4.6%.
Okay, so you got 0.046 in your calculator, right?
And we multiply it by 100.
To convert that decimal to a percent, we can multiply by 100, so we get 4.6% error. And that's how you do it. So it's your error, what you got, minus what you should have got, and then you divide by this accepted value, again, is what you should have got. That's my scientific term, or my redneck term, however that works.
I like the what you should have got.
Yeah. All right. So how come we get errors? By the way, I want to point out that an error is not the same thing as a blunder. If you're in the lab and you spill something, or you forget to calibrate your instrument, or you screw up, then that's a mistake, not an error. If you do that kind of error, go back and fix it.
Redo it.
Yes, redo the lab. All right, the first one is your instrument, right? There's a limitation to what an instrument can measure.
This is the accuracy of your instrument.
Yeah.
Some instruments are more accurate than others. I think you've seen in an earlier podcast where we showed you the accuracy of balances.
Right. And if not, we'll do the demo in class anyway, where you get to see differences in instruments. Yep. Okay, what's another one? You know, we're all humans.
Now here comes a mathematical error. You entered the wrong number, you crossed a number.
Oh no, that would be a mistake.
Ooh, correct.
Yeah, so we would go back and fix this. Personal errors, though, have to do with, like, if you're using a stopwatch, you're going to click start, stop.
What finger you use, how you have the stopping point.
Right. That's why in track they've gone to a lot of automatic timers.
You bet.
Because personal error is a factor. And if you're going for a world record,
Hand time versus electronic.
Yeah.
Only electronic counts.
All right, now let's look at environmental error. Temperature, light, humidity, air pressure. Sometimes that will influence your results.
You bet.
Yeah. If you're out in the field, sometimes picking a sunny spot versus a shady spot will influence the information you collect. And then here's the stuff we have no control over. Random error. Where suppose that you're trying to react sodium and chlorine to make sodium chloride. Then in PE class, if you want to choose teams and have everyone sort of group up in a certain way, you would say, all right, all of the sodiums line up on this side, and all of the chlorines line up on this side, and so now I need one of you and one of you over here, right? We can't do that in a beaker.
No.
In our beaker full of chemicals, we might have a sodium collide with a sodium, and that's not going to make the right spot.
It doesn't hook up.
Right, and that's random error. We don't have any control of that, but that's why we do more than one trial. So on the average, we get better results. All right, time for the calculator lesson.
Here's a tough one.
Yeah, some calculators are simple, and some are really simple. The abacus, that was in the good old days. Some are more complex, and now the TI Inspire is like a little computer in your hand. And then sometimes you might resort to fingers. Yeah.
I prefer that TI-83 though. That's pretty good.
I like the 83s, the 84s, and I'm getting better with the Inspires. So bring what you have, and I'll make sure you know how to use it. You might have to read your user manual, right? Or do a lesson online. But we'll show you what you need to know in our class. If your calculator's a big fancy one, then there's a better chance of you messing up.
Only get what you need.
Right. And in my chemistry class, you need a scientific calculator. Graphing calculators follow the order of operations. Do you remember this from algebra?
So if you don't know them, you're going to be in trouble with this calculator. You better know the uses of parentheses as well.
Parentheses, exponents, multiply, divide, add, subtract, PEMDAS. Please excuse my dear Aunt Sally is how I was taught. That's what graphing calculators follow. So if you don't put your parentheses in the right place, it might do an operation you didn't mean for it to do. A simple calculator, like one without trigonometry functions on it. It's just going to do the operations as you put them in from left to right. Okay, so here's what I want you to look for on your calculator. Get your calculator in front of you. Hit pause on your recording right now if you need to. Look for this button. EE is usually right above the number pads. And it's usually like yellow or green because you have to use the shift button on it. You might see EXP. Yeah, mine says EE. Or you might have EEX. These are more common for a Casio calculator. Or you might have something that says times 10x.
I don't see it on your calculator. You show it?
Yep, it's right above the number pads, the yellow EE. Got to push shift to get to it. All right, so if you have a Casio calculator, then it's your responsibility to know where to find these things. If you don't have an exponent button, you have to do this by hand. Bummer. Okay, so let's put in this number into a calculator. So you're going to push in the calculator 4.56 times 10 to the 8th. So if you push the times button, you're going to get the wrong answer because that changes it from exponent operation to a multiply operation. Remember PEMDAS? This needs to come first, and if you put it here, then you're going to get the wrong answer. All right? So you're going to enter the 4.56, then push the E button. And in my calculator, you have to do second and then comma, I think is what the buttons look like. Yep, second and then the little comma button. And then you just put in the exponent as it's shown. So you push EE, then 8. If you push the multiply button, you'll get the wrong answer. So that times 10 is assumed, it's not shown. All right, let's see. Let's try this out. Now we're multiplying two numbers. So I want to be clear. We have this value times this value. All right, here's what you're going to do in your calculator. You enter 2.43. Then my EE button was, again, second, and then the comma, and then the number 23. Now we use the multiply button. That times button is your multiply button. And then 7.30, and of course, to get the answer, you have to hit enter. Right? All of our students probably know that.
Should we do one kind of the old-fashioned way?
The old-fashioned way?
2.43 times 7.30 and then move the decimals and add it to it?
Yeah, so when we're doing this by hand, here's what you have to do.
Take
2.43 times 7.30. Luckily, we've got a calculator to do that first.
That's correct. And our answer is 17.739.
Okay, always ask yourself, does this make sense? 17.739. So we had somewhere near 7 times somewhere near 2, which should be near 14. And since both of our numbers were a little bit more than that, we should have more than 14. And we,
Pretty good.
all right, now what's our exponent going to be?
Still times 10 to the 23rd.
Right. When you multiply two numbers, you're going to add the exponents together. That's 10 to the 23, and this one doesn't have any. So it's 0.
10 to the
10 to the 0.
which is still 10 to the 23.
Right.
But the scientific notation is not happy now, so we're going to
We
have
have to
to
fix it.
yeah, we're going to have to move it to a number between 1 and 10. So it's going to be 1.7739.
And since I moved to the left, that makes my exponent larger. So it's 10 to the 24. Right? Left makes larger. They both start with L. Moving left makes it larger.
There we go. Now, do we have to go back and talk about the significant figures here?
We will. We haven't done that yet in my notes, but I'm limited here to 3 sig figs, and here's 3 sig figs, and so my answer should stop there after 3.
So our correct answer is just 1.77 times 10 to the 24.
Good deal.
Okay.
And then put a box around your answer so we can find it. Because that's the way I like it. Hey, that's what my answer
You're a
is
genius.
too. Wow. It's amazing. Okay, well that's it for Using scientific notation and working with certainty.
Precision and accuracy.
Yep, in order